This is the first section of chapter 7, which is methods in differential equations. And this section is all about first order differential equations. Now you would have first met first order differentiations in Pure 1. So the very easiest ones are differential equations where you have something like dy dx equals a function of x, and the question said find y. So the way that we'd solve those is that you integrate both sides, and we know that this cancels out, basically just leaving you with y equals something. Okay, and then you'll have like your plus c at the end, and by substituting in values we can get the value of c. So that's the easiest type. Then in Pure 2 we would have met differential equations, so dy dx equals, so it's not just a function of x, but there's also a function of y, and we use the method of separation of variables to solve these. So we would rearrange this so that we've got all the y terms on one side, all the x terms on the other. So we'll have something like 1 over the function of y dy equals the function of x dx, like this. And like before, we integrate both sides, and then once we've integrated both sides we would rearrange to get y equals something. So again we're finding y. Now in Core 2 we go to the next step and we're looking at solving differential equations of this form. So these can't be solved by separation of variables. Like this, and we solve by using something called the integrating factor. So we actually multiply each term by the integrating factor to solve. Now I'm going to go through the proof of that later on. We'll just start by working through some examples of these types here, and then an introduction to this type, and then I'll go through the proof. Okay, so here it says find a general solution to this differential equation. Sketch the members of the family of solutions of solution curves represented by the general solution. So the first thing, the general solution, means that this is a solution that contains plus c at the end. And sketch the members of the family of solutions or solution curves. This basically means the graphs produced by different values of c, by different values of c. Right, so this type can be solved by the separation of variables, which means put all the x terms on one side, the y terms on the other. So if we do that and rearrange it, we'll have 1 over y dy equals negative 1 over x dx. Now we could keep the negative over this side, or we can move it over that side. It doesn't really matter too much. Now I'm going to integrate both sides. So integrate 1 over y dy with respect to y. The other side I'll move the minus over to the other side of the integral sign. So I've now got this. This should be easy to integrate. So I will get log y, and I'll put a modulus sign because I want y to be positive. I'm going to ignore any negative signs. and then on the other side it's going to be negative, and again that will become log x, and I need a constant of integration, so I'll put my plus c at the end. I'll move the log x to the other side like this, and that's going to equal my constant c. Now since I've got a plus here, it means that I'll have the natural log of x times y, or y times x, like that, equals c. Then if I do e to both sides, raise each side to the power of e, I will just end up with, let me write this as xy, modulus of xy equals e to the power c. Now we should know that this is a constant, e to the power c, because c is a constant, then e to the power of a constant is still a constant, so I end up with the modulus of, let's give it another letter, let's call it a. So all I've done here is say, right, let's give that a constant, a single letter, and let's call it a. Now you may or may not recognize this. It's the reciprocal graph, and what I'm going to do is to write this out fully. So remember, when you've got modulus like this, it means that either the answer here could be positive or negative, but this means just take the positive. But if I break it up, I've actually got this. So a positive value equals a, or a negative value equals a. Then if I rearrange them, this might be a bit more familiar, that y equals a over x, or y equals negative a over x. And these are the graphs that I'm going to draw, or the family of solution curves. So I will start with a reciprocal graph, and basically if I were to draw this, a graph representing that is going to be something like this. Yeah, and then if I draw this one with a negative, then that's going to be like this. Yeah, when you have that negative sign in front there, then it's the same as reflecting in the x-axis. So I've just taken the graph that I drew of y equals a over x, reflected it in the x-axis, and as you change these values of a here, that's going to stretch the graph in the y direction. So I just need to draw what the graph might look like as it gets stretched in the y direction. Assuming a is bigger than 1, if it's smaller than 1, then I will end up with sort of curves closer to the axis. So these are what we call these family of curves. These represent all the different graphs we can get if we change the value of a. Okay, this one says find the general solution of this differential equation. Now, on this one, you'll notice we can't solve this by doing the separation of variables. But with this, there is something special about this. If you have a look at this here, this is actually what we get after we differentiate using the product rule. So I'll just remind you that the product rule for differentiation is when you differentiate a product with respect to x or something like this, then we end up with u dv dx plus v du dx, or you could write it as u v dash plus VU dash, something like that. And this actually matches up to something that was differentiated. Now if I call this bit U, then this is U dash. If I call this bit V, this bit is V dash, and there's a plus sign in the middle. So where did this come from? This came from differentiating this. Or if you differentiate this, uv, which is x cubed y, you get that. So these two are equal. Yeah, they're equal to each other. So what I've done here is I've said, okay, I recognise this is what I get after differentiating this. So actually that expression can be written as, well, what you get after differentiating x cubed y, and you can check it. It would be u, which would be x cubed, v dash, which would be dy dx, plus u dash, which would be 3x squared, times by v, which would just be y equals sine x. Now to solve this, we will integrate both sides, like this. And any time you get, I should put a dx at the end here. Yeah, I was going to say any time you get an integration sign and d next to each other like this, because this basically means integrate, differentiate, they cancel out, and then these dx's cancel out as well. So this will be sine x dx. So this cancels out, this cancels out, just leaving x cubed y equals what we get when we integrate sine x, which will be negative cos x plus c. Then the last step is just to make y the subject, so I divide everything by x cubed. So I'll have y equals negative cos x over x cubed plus c over x cubed. Now, unlike the previous example, I can't change this to another arbitrary constant and just say, right, let's c over x cubed equal a, because x cubed isn't a constant. This will vary. So don't be tempted to change that to a single letter. We can't do that, because all parts of this expression must be constant for you to be able to do that. So in this particular example now, this would be our final answer once we've used this method here. Okay, so we're going to be doing a proof, and this proof we want to show that if we want to solve differential equations of this form, then we'll multiply each term by this special thing here that's called the integrating factor. Now let's have a look back at the last example that we did, and we were able to solve it. We had x cubed dy dx plus 3x squared y equals sine x, and we were able to solve it because this matched up with u, this matched up with u dash, this bit matched up with v dash, and this bit matched up with v. So basically it was what we get after we differentiate this product, x cubed y. When you differentiate that product, you get sine, you don't get sine x, but you get this thing up here. And then the next step was to integrate both sides, and we're not far off solving it once we have integrated it. So it's really useful if we can get these first order differential equations to look like this in this format. Okay, so we basically, what we want, let's write this down, so we want a differential equation to look like this, a function of x dy dx plus the derivative of that function y equals another function of x that we'll call, for now, g of x. So this is what we want to get. And the reason we want that is because then all of that left hand side, this side here, so I'm not sure why I put that arrow there, don't need that, we can change to, it's the derivative of f of x y. Yeah. Right, so let's start with a differential equation. Consider a first order differential equation, the differential of the form dy dx plus p of xy equals q of x. Okay, so differential equations that look like this. How can we make them look like this? Well, the first thing that we'll do is we'll times both sides by f of x. So if I do that, I'll get f of x dy dx plus f of x p of xy equals f of x q of x. Okay, now this thing that we've multiplied here is given a special name. It's called the integrating factor. Integrating factor. And what we're going to do is to work out what that integrating factor is. We're going to work out what does f of x need to be so that we can turn a differential equation that looks like this and make it look like this. So if I compare what I want with what I've got, so here, that's fine, that's the same as this. Yeah. But the next part, this f dash of x, needs to equal this for this to work. Now the other side's not a problem because that's just a function of x and this is just a function of x here. This is the bit I want to try and work out. So we can now write down that really I want f of x times by p of x to equal f dash of x. And we want to find f of x. So the first thing that I would do is if I divide both sides by f of x, I'll get f dash of x over f of x equals p of x. Then I'm going to integrate both sides with respect to x, like this. So that will give me, well, whenever I've got the derivative of something over itself, that's just log x, or log of the bottom. So I've got the log of the bottom equals what I get when I integrate p of x with respect to x. Now if I raise both sides to the power e, like this, what I'll get is f of x equals e to the power of the integral of p of x dx. And this is the important bit here. So this is how we find the integrating factor. So this is the integrating factor. So if we take our differential equation that looks like this and we multiply every term by the integrating factor, which we find by doing e to the power of the integral of p of x, which it will be the function that you see in front of y, then it turns it into this form, which means we can then use this method of like reversing the product rule basically. Yeah, so this is the proof of that method. Okay, so this one says find the general solution of this differential equation. So if I were doing a question like this, the first thing I would do is to write down the form of this equation. Does it match up with this form of a differential equation? Yes, it does, because p of x would equal -4 and q of x equals e of x, so it matches up. So the first thing we need to do is to find the integrating factor, and we do that by doing e to the integral of p of x dx, which means doing e to the integral of -4 dx. So if you integrate -4, you'll end up with -4x, so you have e to the power -4x. Now there's no plus c here, so that means taking every term of this and multiplying it by e to the power of -4x. So we'll do that. So I'll just write down times all terms by e to the -4x. So I'll have e to the -4x dy dx minus 4e to the -4x y equals e to the x times by e to the -4x. Now using the product rule in reverse, I can see that this bit is like u, this is u dash. Yeah, if you integrate e to the -4x, you'll end up with -4 e to the -4x. Then that means that this bit here is v dash, this bit here is v, and then this can be simplified by adding the powers. So I'll have e to the power of -3x. So using the product rule in reverse, what we'll have is the left hand side is what you get when you differentiate uv, so e to the -4x times by y, and that will equal e to the -3x. Then we're going to integrate both sides like this. So this should be a dx after this side, like that. So on the left hand side, we know that these are going to cancel out, just leaving e to the -4x times by y equals, now when we integrate e to the -3x, remember reverse chain rule means you integrate the outside so it stays as e. The inside of the brackets, which will be -3x, doesn't change, and then you divide by the inside differentiated. So we're going to have -1/3, and this is going to be plus c like this. So the last step will just make y the subject. So y equals -1/3 to -3x divided by e to the -4x plus c divided by e to the -4x, and we'll tidy that up, and we'll have here, when we subtract -4 from the power, it'll be like -3 minus -4, so that'll be like -3 plus 4, So that'll be plus 1 as a power, so negative a third e to the x, and then the negative power, I could bring that up to the top and write that as e to the 4x times by c, my constant of integration. Whoops, and I should write that y equals that, not just an expression, it's an equation. So there we go, that will be our final answer, and we've used this integrating factor to solve that first order differential equation. Okay, so in part A we're asked to find the general solution of this differential equation, and then in part B it says find the particular solution. So just as a reminder, the general solution in a question is where you have the plus c or something at the end. So general solution will be something where you've got y equals something plus c, and c is our arbitrary constant. Okay, so that's a general solution. For the particular solution, this is where we find c. So we work out the value of our arbitrary constant by substituting in values of x and y by substitution of what we call the boundary condition substitution of x and y, and these are called boundary, let's do that on a fresh line, boundary conditions. So just some terms you need to beware of: general solution, particular solution, and boundary conditions. Right, so part A, let's see if this first order differential equation matches up with the form that we want, which is dy dx plus p of xy equals q of x, and it does, because I would have this, and I'll need to divide everything through by cos x to make it look like that form. So if I do that, I'll have dy dx plus 2y sine x over cos x equals, that'll be cos cubed x. So I've divided everything by cos x to make it fit this pattern over here. So then I can say that p of x will equal 2 sine x over cos x, which is basically just 2 tan x. Okay, and I need that because I now want to find the integrating factor. And the integrating factor, that's going to be e to the integral of p of x, so the integral of 2 tan x dx. I can move the 2 over, so I'll get e and then 2, then the integral of tan x dx. Now from the formula book you'll find that tan x integrated is a log sec x, so this becomes e to log sec x. Okay, so that's from the formula book. When you integrate tan, it becomes log sec. The 2 at the front, which is here, we can write as a power, so that will enable us to cancel out the e and a log. So I'll have natural log sec squared x. So these cancel out. So my integrating factor will just be sec squared x. Sec squared x is my integrating factor. So that means multiplying every term in this. So that will give me sec squared x dy dx plus 2y. Now the sine over cos is tan x. Sec squared x equals cos cubed x sec squared x. Now remember, a little tip just to help you out, is that the thing next to dy dx, that's always going to be the u part, yeah, and then the y on its own is going to be the v part. It's always the case. So the bit next to dy dx, all of that will be u, and everything apart from, or you can say just the y, is u. So the 2 tan x sec squared x, all of that is u dash, and this is v dash, but we don't want those. We want to say that actually all of this statement on the left is what we get when we differentiate uv, which is sec squared x y. And that's going to equal the right hand side here. Now this cancels out because remember sec is the reciprocal to cos, so what will happen is that will cancel out with two of the coses, just leaving cos x. So write that down like that. Now we'll integrate both sides. Whoops, keep forgetting to put that dx. Like this. And then we know that on the left hand side the integration and the differentiation there cancel out, just leaving sec squared xy, and cos integrated is going to be sine, so sine x plus c. We want to make y the subject, so we can divide both sides by sec squared x. So we'll have y equals sine x over sec squared x plus c over sec squared x. Now we could, if we want to, get rid of the sec squared x, because when we come to use it on our calculator we'd probably want that as cos squared. So if we take this to the top, that will become cos squared. So it's the same as sine x cos squared x plus c cos squared x. Okay, so there's our answer for part A, which we're going to use for part B. Now part B is just a matter of substituting in y is 2 and x is 0 to find c. So let's just create a bit of space up here, shouldn't be too difficult to do, and we'll do part B. So we'll substitute in 2 and 0 into our answer, so I'll have 2 equals sine 0 cos squared 0, whoops, not theta, plus c times by cos squared 0. So we can easily solve that, since all of this bit here is just going to be 0 because sine 0 is 0. All of this bit here is going to be 1 because cos 0 is 1 and that squared is 1. So that means that c is 2. So that's the value of our arbitrary constant. Now we can write down our particular solution, which is going to be y equals basically what we had before, but with 2 at the end. So sine x cos squared x plus 2 cos squared x. And I suppose if you want you could factorise that and write it as y equals cos squared x sine x plus 2, but I'm guessing it doesn't really matter if you factorise it or not. So there's our answer for part B, our particular solution, because we've worked out the value of c. So you should now be able to do exercise 7a on pages 151 to 153. So let's just talk a bit about solving first order differential equations. So we have the separation of variables when we have a differential equation that looks like this: a function of x times by a function of y. Then if we notice that we have a differential equation that looks like this, in this form, okay, so what we use is the product rule in reverse. Yeah, because we know that we can write the left hand side as the derivative of f of x y. Now if it's not in that form, then we would use the integrating factor. We multiply everything by the integrating factor, which is e to the power of the integral of p of x when our differential equation is in the form dy dx plus p of xy equals q of x. So 3 slightly different methods.